You have the skills because we don't. Yeah, like the internship report is the kind of. Oh yeah. Yeah, en fait, internship report is.
Okay. So welcome back. So what we did just before the break was to formulate everything in complex space. So our variable q tilde can now be represented as the real part of some q0 hat, which is a complex function, times an e to the I lambda t, which is also a complex function. So in the end, we just need to take the real part of this. And now what we would expect from that is that we can actually analyze this e to the actually the I here is too much. It should not be e to the I lambda t. It should just be e to the lambda t. That we can realize that it's actually the e to the lambda t that tells us whether we have something that grows exponentially or decays exponentially. And okay, and so how can we do that? Well, the idea now is that we can decompose this e to the lambda 2 in actually two parts, into a real part and an imaginary part, because the lambda per se can be a complex number here. So we can then say that this is e to the sigma times t times e to the I omega t. So that means essentially that we just decompose lambda into sigma plus I omega. So we treat lambda as a complex number, with sigma being its real part and omega being its imaginary part. So this is actually a complex number. So that means that actually the sigma and the omega have two different, let's say, two different purposes for the final solution here. The sigma here would take the position of a growth rate, because if you look at its contribution to e to the lambda t, it would just be e to the sigma times t. So this would determine what the asymptotic fate of our solution will be. Either if sigma is larger than 0, it would be infinity. If sigma is lower than 0, it would be 0. The omega here essentially has a different purpose. This essentially is the angular frequency of our solution. So it will, in the e to the lambda t, it would just be e to the I omega t. And of course, you know what the solution e to the I omega t is. It essentially just goes round and round and round on a circling complex space. So this would be an oscillation. So if I just draw this, as we have done, it's very similar to what we have done for Stokes' second problem. So if I draw this for two different situations, this one would be for sigma larger than 0, this would be for sigma lower than 0, and omega being kind of something that is non-zero, just to have something a bit more interesting. So if you have sigma larger than 0, so something that is growing, we would probably have something like this, where kind of the envelope of this would correspond to my growth rate e to the sigma t. And of course, the kind of the oscillation comes from the e to the I omega t part. And of course, at the same time, if we look at the stable situation, when sigma is lower than 0, we would start somewhere large, and then we would get smaller. So something like that. And of course, I should write here that this is, of course, a function of time, and what we plot is q tilde. And of course, the left side would be the unstable case, and this here would be the stable case. And of course, somewhere in between, you would have, if I just to be complete, if I have something where the amplitude is always the same, so it look like this, this would be the situation where sigma would be exactly 0, and this would be the neutral case. Q tilde, and this would be T. Okay, so I guess this is nothing very strange here, but of course it still remains for us to determine what is actually the value of lambda, because now we have seen that by knowing lambda for a specific problem, we can determine both the growth or decay, and we can determine the angular frequency of the solution. So the question now that we have is how to determine lambda. Well, we know how to do that. Our ansatz was to say that our Q tilde is Q hat times e to the lambda t. So this is what we said that we want to do. And of course, now what we can do is we can just take this ansatz and put it in our dynamical system that we had from the beginning. So we just write dq tilde, or we take the system d, which was dq tilde dt, and we feed that into that, which then becomes q hat times ddt of e to the lambda t. And of course, this derivative you can actually do because this is simply, it's an exponential, and we need to do the derivative with respect to t. So what we get is lambda q tilde e to the lambda t, or we can also say that this is just lambda times q tilde, because of course this here is again the same as here. So this would be the time derivative of our dynamical system. So dq tilde dt is nothing else than lambda times q tilde. And of course, this is kind of nothing very surprising. In the end, this is just a Fourier transform. So this is essentially a Fourier transform in time that we have performed. So now we look at the complete system. So we introduce it there. And of course, what we get is, or the system was dq tilde dt, which was 2qb minus a times q tilde. And this was what we called j times q tilde, if you remember from before. Now with our new ansatz that we have just introduced, q tilde being q hat times e to the lambda t, we can write that this is j times q hat times e to the lambda t. And from what you now know from the time derivative that we have just calculated before, this would be lambda times q hat e to the lambda t. And of course, now we see what this will be ending up with. In the end, this here leads to j times q tilde, which should be the same as lambda times q tilde. Right, I can divide by e to the lambda t. So if we now do this Fourier transform in time, our dynamical system has become j times q tilde being lambda times q tilde. And of course, this is actually quite interesting because we can use this equation now to calculate what q tilde is, or to isolate the q tilde. So this becomes something like this: j minus lambda. Actually, I should write that in black. Sorry. J minus lambda times q tilde is 0 if I just take everything on one side. Now, of course, there's one little aspect here. If we talk about vectorial quantities for q, which I've introduced in the beginning, that it could be vectorial quantities. I have here a vector or a matrix J minus a lambda. And of course, that doesn't really work. So that means I need to have here an identity matrix. So for vectorial quantities. Okay, so now this equation here at the end, I can use to calculate either J or Q. So you see that Q and lambda and Q, they actually belong together. So for a specific Q, I get a certain lambda and vice versa. And of course, all is kind of governed by J, the Jacobian of the system. And of course, this type of equations, you very well know what that is. When you have, a scalar value and the vector kind of belonging to each other, this is nothing else than an eigenvalue problem. So we obtain an eigenvalue value problem in terms of Q tilde, which is the eigenvector then, and lambda would be the eigenvalue. It is also, what we can realize from here, it is also a homogeneous problem. Homogeneous means that there's actually a zero on one side. So it's not a forced problem where we have some external input. Lambda in this case would be a complex number, of course, but it is a scalar. It's complex, but scalar. And always when you have a homogeneous eigenvalue problem, the solution of that could either be kind of the trivial solution, and in this case the trivial solution would just be Q hat being zero. Of course, that would fulfill the homogeneous eigenvalue problem. But of course, that's not extremely interesting. The more interesting solutions to our problem would come from essentially calculating the eigenvalues here. And of course, that just means that the determinant of J minus lambda I would be zero. So in those cases, I would actually get some more interesting solutions where lambda and Q would kind of belong to each other. So what we have now realized with this, if we go into complex space, so we essentially make the assumption that we had here. So we say that our Q tilde, so our disturbance, is Q0 hat times e to the lambda t. So we have some wave function, or well, later on we will call that an eigenfunction. So the Q hat and the e to the lambda t, which is then the dependence in time. When we do this assumption, then we end up at the end of the day with an eigenvalue problem where we have, well, actually the eigenvalue problem is this one. Okay. Now, of course, we can, just to finish our example that we had, we can set up this eigenvalue problem and solve it. Now, of course, in our case, we have a scalar problem. In a scalar problem, the eigenvalue problem is not so interesting, but we can still do it. So for our scalar model problem, and we can calculate everything. Our Jacobian was 2qb minus a, and the eigenvalue problem, as I said, it's not extremely interesting because the determinant of j minus lambda I would just be, j equals lambda, nothing else. So that means for us, lambda would just be 2q minus a. And of course, the result here would be for the two base states that we had, 0 and a. In the case of 0, our j would be minus a. And for qb being a, my j would be a. And of course, now from everything we know, because j is being lambda, I should write it like this. Now we know that the real part of lambda determines the growth rate, and if the growth rate is larger than 0, we're unstable. When the growth rate is lower than 0, we're stable. So that means in this case, it's very easy to see just from looking at the lambda that this one here would be the stable case, and this one would be the unstable case. But I guess you see now the kind of the general principle of what we would like to do when also considering hydrodynamics instabilities. So what we do is we start with our problem. We find base states to the problem. So first step was finding the equilibrium state, the base flow. Second step would be the linearization. And then in the third or fourth step, we would calculate the eigenvalues of that problem. And then we look at the lambda, so the eigenvalue, and see whether the real part is growing or decaying. That's essentially our mission from now on. Okay? Okay. So I guess after this this initial model problem, let's now go into the or let's now look at real fluid flows. So hydrodynamic stability. So that's now the next topic. And as I said, we're not doing anything else than exactly what we have done now for the model problem. In hydrodynamic stability, this is also called a so-called local analysis. Local means that we essentially take a certain position in the flow and we do the linearization or the analysis exactly in that point. But apart from that, it's exactly what we did. So it's a local analysis in a sense of we look at the stability of small perturbations to a specific base state. That's what we're going to look at. Just with the difference that now our equations that we need to consider are the Navier-Stokes equations. So we look at those equations, dy dt plus uj dui dxj is minus dp dxi plus 1 over Reynolds d squared ui dxj dxj. So that's the momentum equation, just written, I mean, it's just a normal momentum equation written in a non-dimensional form. Non-dimensional in the sense that I only have the Reynolds number left, so I'm not having a viscosity, but I'm directly in the, I have directly done it in such a way that you have a Reynolds number where I have rescaled all the velocities with a reference velocity, all the length with a reference length, and all the times here, so the t here with a reference, well, speed divided by a length, so reference time. Also, one thing to just be clear about, when I do the non-dimensionalization of the pressure, this is in some way a modified pressure because I have already scaled that one with the density. You know, otherwise I would have here 1 over rho, and then in the non-dimensionalization of the pressure, I would use the density. Okay, and of course to make the system complete, I also need to have the continuity equation. So something like that. So this here is now the system or the equations that I would like to look at. Now, of course, the problem is this is nonlinear. We have the nonlinear term here. So that means we actually need to do the following. So we need to first do a decomposition of our solution, ui into a base state. Ui, I use here a capital letter, plus some perturbation. Now, of course, in terms of the formulation, it's not extremely smart that I was using before a tilde and now I'm using a prime, but the perturbation here, when we do Navier-Stokes, we typically use a prime for that. So we have here the base flow, and this one here would be the perturbation. And of course, I'm doing again the same idea that the base flow would be a state of the flow where the time derivative would be 0, so it's a steady state of the problem, and then I would look at perturbations that are small, so such that I can perform a linearization later on. Yeah, so my base state QB would now be, well, this UI and the specific pressure that is also kind of part of the base state. This is, well, what I just said, the base flow or the base pressure, which is steady. And of course, in that sense, it fulfills the steady Navier-Stokes equations. Fulfills the steady Navier-Stokes equations. Okay, so now I have my governing equations, I have my decomposition. Well, what I need to do now is to insert this decomposition in the governing equations, and I need to linearize. And yeah, so insert into, well, insert the decomposition. So decomposition into the governing equations. Okay, I will do that now here on the with you, just to kind of showing you that there's really just, it's nothing else going on than just inserting it and then linearizing it. So if we do that, so we start with the time derivative, so dy dt, that's for the base flow, plus dy prime dt. Then we have the advection term, where we have uj plus uj prime times ddxj of, again, ui capital plus ui prime. And that should be the same as minus dp dxi minus dp prime dxi plus 1 over Reynolds. And then we just have the second derivatives of both of them. So 1 over Reynolds of d squared ui dxj plus d squared ui prime dxj dxj. So, like this. Well, now you see that most of the terms are actually, good as they are. The only difference is, or the only thing where I need to do something is the nonlinear term, where I actually need to do all the multiplications. So that means, well, maybe a bit lazy here. Let me just copy and paste like this. Okay, so I have the same here. So the only thing that I actually need to look at is, or what I need to do something with is this part in the middle. Everything else is kind of the same. So that means I'm just taking this, moving it a little bit further away. Of course, I realize that when you write it down, you cannot do that. Yeah. So now the only thing is really just to do all these multiplications. So what I get is uj dxj of ui. Then, so that was the first one. Then I have uj dui prime dxj plus uj prime dy dxj, and then I have uj times du I prime dxj. So that's just it's clear. Multiplying these two terms with each other. Now, of course, this was just for the momentum equations. For the continuity equations, of course, I can do the same thing. There I get dui dxi plus dui prime dxi is 0. So that's the continuity equation. Okay. So now let's take out. Wait, there's. What happened here? Something is a bit weird down here. So, like this. Now let's take out the green pen and take away those terms that are actually zero. First of all, base flow is steady. So that means that term goes away. Then I know that the base flow fulfills the steady Navier-Stokes equations. So that means that this term, and this term, they go away because the base flow is fulfilling Navier-Stokes. This one was steady. This is base flow fulfills Navier-Stokes. This one is also going away because the base flow fulfills Navier-Stokes. Of course, that includes also the continuity equation. Well, and then we have one more term that we can take away. That's this one here. And this one goes away because of the linearization. Essentially because we say that ui prime, so the perturbations, are much, much smaller than the capital Ui, the base flow. Because we're only interested in development very close to the base state. Okay, so the next step would be that we include or that we write our perturbation as a complex variable as we had before. So a u hat times an e to the I lambda t. We fill that in. And of course, because it's linear, everything would be exactly the same way as before. In the end, we would get an eigenvalue problem for the lambda, and we solve the eigenvalue problem, and we determine with that the asymptotic fate of our perturbation. Either it will go to infinity or it will go to 0. So that means that the next steps now would be as before. We would get an eigenvalue problem for a lambda, and that will then determine the fate of ui prime. So that's the idea. It's a little bit more complicated than that, and therefore I'm not doing that step just now. The reason why it's a little bit more complicated is because we also have the pressure. And so in order to actually derive the actual equation for the exponential growth, we need to somehow find a way of how to get rid of the pressure, or at least to combine the pressure and the continuity equation. Right. So therefore, I'm not exactly doing the step now. We do that maybe in I don't know, half an hour or so. But the basic principle is the same. Is there something wrong? Maybe it is.
What's it say? Determine the fate?
The fate, yes.
The fate. Okay.
Yeah, I think there was a bit too much here at the end. Fate. Yeah. I mean, what happens with ui prime? Sorry. Okay, but this in the end, that is exactly what we call a linear stability problem in fluid mechanics. That's essentially it. So formulate the linear equations, put in this exponential ansatz, and see what happens. That's a linear stability problem. And of course, what you now see is we actually have one parameter left in there, the Reynolds number. And the Reynolds number would now serve as the bifurcation parameter as we have introduced earlier today. So that means now what we can do, using this, this linearized form, we can, for instance, then monitor when or at what Reynolds number you would suddenly switch from a stable situation into an unstable situation. So meaning at what Reynolds number we would have our eigenvalue, the real part of the eigenvalue lambda, going from negative to positive, for instance. That could be one question that we could ask ourselves. Or that's a typical question that you would ask yourself. So we can use that to find the minimal critical parameter Reynolds or Reynolds C in that case, above which a specific initial condition of infinitesimal amplitude grows exponentially. So that would be now one question that we could ask ourselves, which we can solve or which we can answer using this, this linear stability problem. So we could find the critical Reynolds numbers. Now, I just want to mention or explain two things. I said here specific initial condition and infinitesimal amplitude of this initial condition. So why do I say it in that way? Well, specific initial condition means that would actually be the eigenvector that I get from the eigenvalue problem. The eigenvalue would be the lambda, so the combination of growth rate and angular frequency. That's the eigenvalue. But for each eigenvalue, obviously, I get an eigenvector, which is associated to it. And that would be the specific initial condition that would then have the growth rate given by the eigenvalue. So therefore, these two things always belong together. So therefore, it's a specific initial condition. And then why did I say infinitesimal amplitude? Well, I did a linearization. So I'm actually interested in small perturbations. But of course, because it's a linear problem, amplitude doesn't matter, really. But if you then think of the nonlinear counterpart, of course, it means a small amplitude. So in a linear setting, it doesn't need to be infinitesimal, because you scale out the amplitude anyway, but in a nonlinear problem, it's the infinitesimal disturbance. Okay, so this is the setting. So this is what we would like to do. And as I said, the difficulty here is that we have the pressure. And the pressure is a little bit annoying here because, as discussed earlier, the pressure here acts as a, it kind of acts as a, we said before, it's a Lagrangian multiplier that somehow, so it's a constraint, or rather, the continuity equation is a constraint that is fulfilled with the help of the pressure. So in that sense, the pressure acts as a Lagrangian multiplier that at each step would make sure that the divergence freeness is fulfilled. But in terms of just writing everything in the framework that we had before, where we would like to write the equation, where do I have it? Something like this, dq dt is, something times q. The pressure is a little bit annoying because we actually don't have a time derivative for the pressure. So what we need to do later on is to somehow combine the continuity equation with the Navier-Stokes equations to be able to formulate it anyway in such a way. Okay. But it will do that, and it's possible to do. But actually, what I would like to do now as kind of an insert a little bit, I would look at something else, very briefly. So as a kind of an insert, I would like to ask a different question for a time being. A different question. And the question would be, are there any growing solutions without linearization? So why do I ask this question? Let me just go back very briefly. We said here the linear stability would be this minimal critical amplitude ray C, above which the specific initial condition and so on grows. So here we talk about ray C. If you now again go back to what we talked earlier, to this diagram, ray C would be this one, which would determine whether something is conditionally stable or unconditionally unstable. So that's the position where I would look at this exponential growth of infinitesimally small perturbations. So that would determine the ray C. The question that I have just asked, whether there would be also growing solutions without linearization, that would actually be the question, where is ray G? So as soon as I have some growing solutions without linearization, I would actually go from the unconditionally stable part, where everything decays, into the region where something may grow. So the first question would be, can I do something about the ray G here when I don't do any linearization? So essentially this would be the question about ray G. So how would I work with ray G here? And actually that's quite an interesting, well, obviously it's an interesting thing because otherwise I would not take it up here. But what we will see here is actually quite interesting and also quite relevant for the general understanding of stability. So how could we do that? Well, the way is we multiply the nonlinear equations with just, well, the nonlinear perturbation equations, I should say, the nonlinear equations for uj prime with uj prime. So what are these nonlinear equations? Well, it's essentially these guys here that I had here without the blue crossing out. So I'm just not doing the linearization. I do everything else. I do the split into base flow and perturbation, but I'm just not taking out that term, the blue term here. And then it means that these are still the exact equations. There's no approximation I'm doing. It's just I'm not doing the linearization. So therefore, these would be the nonlinear equations for uj prime, and I'm just multiplying those with uj prime. And of course, now you can wonder what is that? Well, actually, it's quite interesting. What you will get is actually an equation for the energy of the flow. But let's look at this. So if I'm doing that, and I mean, if I just start with the first term, I guess that will show you the principle. So I'm taking these equations, and I'm multiplying it with ui, actually it's ui here. It's not uj, it's ui. Not that it matters because it's just it's a dummy index, but maybe easier to understand. So I multiply it with ui. So the first term, for instance, becomes just ui times dy dt, right? And of course, why is this important? Well, first of all, I'm actually going from a a vector equation, from 3 equations for u, v, and w. If I multiply that with ui, I actually, afterwards I do a summation over the i's. I actually go from a vector equation into a scalar equation. The second thing that you can directly see, I guess, is with the continuity equation, I can actually take in the ui into the time derivative. Right? So that means that I will actually afterwards have an equation d dt of ui, or ui squared. And that is the energy, that's the kinetic energy. So that means the idea why I'm doing this multiplication is that I will get an equation in the kinetic energy, and of course that's exactly what this rate G is all about. I would like to find out, is there anything that grows? And if there is anything that grows, it of course means that the energy needs to go up. If it doesn't grow, the energy needs to go down. So that's the purpose of what I would like to do. Okay, so I just need to multiply all the terms that I have left here with ui prime. And then I will see what happens to all my terms that I have left. So, actually there should be primes here, of course. Yeah, so let's do that. So next term, ui prime, it was uj, that was the mean, times dui prime dxj. Then I have ui prime uj prime dui dxj. Then I have ui prime uj prime dui prime dxj. You see, this is the nonlinear term, which I keep because I'm not doing the linearization. And then on the right-hand side, I have minus ui prime dp prime dxi plus 1 over Reynolds of ui prime d squared ui prime dxj dxj. Something like that. And well, now it actually turns out that I can work a little bit on these terms to actually make them into a form that actually will tell me something. So if I call this term number 1, I call this here to be term number 2. Then I have this guy to be term number 3. Then this one would be term number 4, and then I have this as being term number 5. This one, term number 6, I cannot do anything with, so I will not even do anything. So let's start with term number 1, because that's what I just mentioned before. Now I can just do it formally. So I have dui prime dt. And then now I can exactly do what I said. Together with continuity, this will just be d dt of half of ui prime ui prime. And of course, this ui prime, this is an energy. So I can say this actually becomes d dt of the kinetic energy E, and this E would be the kinetic energy. Energy E being 1/2 of ui prime. It's the energy of the perturbation, of course. Okay, so that means what this will give me in the end will be the evolution of the kinetic energy. And now we need to see what we can do with all the other terms. And well, that's of course a little bit tedious, but well, we can quickly do that. It's always the same idea that we apply. So it's nothing really complicated. So for instance, this term, that's term number 2, that's the one with the pressure. I can do the same trick with the continuity. I can take in ui prime into the derivative. So I get ddxi of ui prime p prime. And then in the sense of the continuity, or of, well, in the sense of the product rule, I'll get p prime dui dxi prime. That's, of course, exactly what I said. This is the continuity equation, 0. So that means that this term simply becomes d dxj of uj prime p prime, something like that. What you have seen now, what I can also do, of course, that's a typical thing. Here I did everything in terms of I.
I covered it.
Huh?
I covered it.
Ah, there's a trick there. Okay. Okay, last sentence. So this one here was written in terms of I, but as you know, this is a scalar, so this I acts as a what we call a dummy index because it doesn't really appear. So I can go from I to j. You see what I mean? Okay, so this was the second term, and I guess then we take a break now, and afterwards we have 3 more terms to go, and afterwards we can put everything together. Okay, so let's have a break.